Okay, we're going to continue on here. We're into the big chapter 14. So 14 is all about acid and bases, equilibrium, and we'll continue on and talk about buffers and titrations later in this chapter. But earlier we started talking about really acids and bases, and remember that acids are really anything that can produce H plus or really H3O plus ions in solution, while a base is really anything that will produce hydroxide ions in solution. Remember, in acid-base chemistry, as we talked about, H plus and H3O plus are pretty much the same deal. They represent the acidic part of the solution. We talked about a Bronsted-Lowry definition of an acid and a base, where an acid is a proton donor. And remember that a proton is an H plus, so that's another name that we use in acid-base chemistry for H plus, which is a proton. A base is a proton acceptor. And as we talked about, you got to remember that it's not just the H, but it is the H plus. So the charges of everything does change as somebody obviously accepts an H plus or removes an H plus from solution. The sort of consequence of Bronsted-Lowry definition is we get partners that sort of occur. So when we have an acid and a base on one side of the arrow, it creates some partners, which is the conjugate acid and the conjugate base. And the relationship is the acid on one side is partnered up sort of on the other side with the conjugate base, and the base on one side, its partner is the conjugate acid on the other side. Remember that for these guys to really be pairs, as we talked about, the only difference that there can be is one H plus. So there can only be a one H plus difference. So when we have the acid here, it's going to lose the H plus. So our conjugate base would have one less H plus than it started with. Our base will accept it. So the conjugate acid will have one more H plus than it started with. So again, that is definitely the relationship between our acid, base, and conjugate pairs. And remember that pretty much on the left-hand side of the arrow there, it's going to be your kind of run-of-the-mill acid and bases, if you will, and all your conjugate partners are usually on the right-hand side of the arrow. We got into the idea of the equilibrium of water, which is sometimes referred to as Kw, and that is the concentration of H plus times the concentration of OH minus. And at 25 degrees Celsius, it does equal 1 times 10 to the minus 14. Remember, again, here you could swap out that for the H3O plus concentration. That is what we could use to calculate either really the H plus concentration of the solution or the acid part of the solution, and also the base part of the solution, which is the OH minus. The relationships of those guys is pretty much as one goes up, the other goes down. So they kind of work in opposites of each other. So as the H plus concentration goes up, the OH minus concentration will go down. And as the H plus concentration goes down, you will see the OH minus concentration increase. So by comparing the concentrations of H plus and OH minus in a solution, you can determine whether or not the solution is acidic, basic, or neutral. Obviously, if our H plus concentration is greater than the OH minus concentration, we are looking at acidic. If our H plus concentration equals the OH minus concentration, that is neutral. And that also would be 1 times 10 to the minus 7. And if our H plus is actually less than, or our OH minus is greater than, it would be basic in that case. The good news is it is really the same calculation regardless of which one you are calculating. You basically take Kw and you divide it by the other concentration that's given to you. We then got into, at the end, I think, the pH scale. And the pH scale does run from 0 to 7 to 14. Again, less than 7 is acidic, above 7 is basic, and really there on 7 is neutral. As you go from 7 again towards 0, you become more acidic. As you go from 7 to 14, you become more basic. And we do calculate the pH scale, or the pH of a solution by taking the pH is equal to minus the log of the H plus concentration. And once again, you could use H3O plus there as well. We talked about a couple of things in terms of calculating, depending on the type of calculator that you have. Again, if you have a display calculator, you would enter it in exactly the way the formula is written. Negative button, not the subtract button, which is sometimes a common mistake people make. So make sure you use your negative button, log, and then most likely use your concentration, and you make sure you use your exponent button when you punch it in. If you have a non-display calculator, you do need to go backwards in this formula and pretty much all other formulas that we're going to see in this chapter. You would start with the number, you then would hit log, and then you would hit the negative button really to turn it into a positive number. You should always use the pH value to determine whether it's acidic, basic, or neutral. And as we'll talk about, there is, again, only one answer for that, is acidic, basic, or neutral, not all three for the same solution. We talked about the idea of how many decimal places you should take the pH value to. And remember that in this case, if you're calculating something like pH, the number of decimal places in your pH is equal to the number of significant figures in your concentration. So we're going from really significant figures to decimal places when we're doing this, and vice versa. If you had the pH and wanted the concentration, the number of decimal places in the pH value would be how many significant figures your concentration should have. So again, it's not sig figs, it's sig figs in terms of this. Sig figs to decimal places is what we're looking at. Any questions on any of that stuff there we talked about last time? Okay, then I think we're about at this slide, I think. So we talked about the pH, obviously, equation. There is a similar sort of scale, but it measures OH minus concentration, and that's what's referred to as the POH. And the POH is equal to minus the log of the OH minus concentration. Again, not to be confused with the pH, which is minus the log of the H plus concentration. The name actually tells you what you need. pH, you need the H plus. POH, you need the OH minus concentration. Why that's kind of nice is there's a nice relationship between pH and POH. If you take the pH plus the POH, it will equal 14. So if you have just the hydroxide concentration, you could calculate the pH, POH of that solution, and then simply subtract 14 from it, and you would have the pH pretty easily. If we add in a couple other sort of calculations that we will sometimes see, if you do have the pH, you could get the H plus concentration from that. And the H plus concentration would equal the inverse log of the minus pH. Now, most people's calculators, when they hit the inverse log, that's like the 10 and the caret is usually what pops up. And then you want to make sure it's negative pH in this case. Usually to get the inverse log on most people's calculators, that is the upper left corner. There's usually a button like shift or second button up there. And then usually above the log button, you'll see this 10 to the X, which might be how you've been doing scientific notation incorrectly, but that's actually what you use it for, is the inverse log is actually that button there. You could also, if you have the POH, you could get the OH minus concentration from it. It's the exact same calculation. It is the inverse log of the minus POH. And once again, that most likely will look like a 10 and a caret, POH on there. If we add in our other one that we talked about just a second ago, which is our KW, equals H plus times our OH minus concentration equals 1 times 10 to the minus 14. This does give you a variety of different ways at which you can actually solve a problem. So there is kind of more than one right path depending on sort of what you choose. As long as you choose sort of a correct formula and equation and pathway, everybody should get to the same place, maybe a slightly different with a little bit of rounding, but should pretty much end up the same how you do it. So in some cases, you may not even have to use KW. You can just kind of use the inverse log. But if you want to still use KW, you can as well. So there's a variety of ways you do it. On the left-hand side here is a pH scale. And again, we see some things. We got some HCl, some acids down here, which obviously are acidic. Up here, like we talked about, is kind of cleaners, and sodium hydroxide is basic. We have pure water here, which is about 7. If I take water that's maybe not pure water or water that's been sitting out, say out on the countertop in your beaker, will the pH be 7? It will not. It actually will be like acidic. It'll be like in this range probably. And that's because it picks up some carbon dioxide from the air, makes some carbonic acid, increases the H+ concentration in the solution, and lowers the pH a little bit and stuff like that. So sometimes people are surprised when they take this guy here, which is a pH meter, and they're surprised that when they stick it in there, my water is like kind of acidic there when they do it. So a pH meter measures the pH of the solution. It really measures the H+ concentration that's floating around in that beaker. In reality, what it really measures is kind of the voltage that you tell it, like this is a pH 7, this is a pH of 10, this is a pH of 4. And then it does sort of a calibration curve and figures out by the voltage of what it sticks into your solution, what the pH would be after you calibrate it. That's obviously a very good way to do it. We'll start using those pretty soon in the next couple of experiments. But it's a good way to just gives you the pH straight up what it is. Other ways we could get the pH is we could use something like pH paper. pH paper, you dip your solution onto the paper, changes color, you kind of move it around to match up the color on the paper to the chart. If you maybe have a pool, ever did any pool care, they're kind of like those little test strips you put in the pool and it all changes color and you kind of check everything. We also use litmus paper sometimes. It doesn't give us an actual value for pH or anything like that, but we do use litmus paper to tell us if it's acidic or basic. And a reminder that if litmus paper turns red, it's acidic. And if litmus paper turns blue, it is basic. So again, it doesn't give you obviously a pH value for it, but it will give you an idea as to whether or not your solution is acidic or basic. All right, any questions on any of those there? All right, let's try some here. The pH of rainwater collected is about 4.82. Let's answer a bunch of questions here. Let's do, like it asks, what is the concentration of H+? What is the concentration of OH-? What is the pOH? And is it acidic, basic, or neutral? For the second one, we have the OH- concentration is 2.5 times 10 to the minus 7. Let's do what is the pH, the pOH, the H+ concentration, and again, is it acidic, basic, or neutral? All right, so take a couple moments there for each of those and see what you come up with. Make sure you understand how to properly punch them into your calculator. All right, let's take a look here and see how we're doing. So in this case, we do have the pH given to us on the first one. So we have a pH here of 4.82. This does give me a couple of options. I could do the inverse log to get the H+. I could also get the pOH really easily. So I'm going to start with the pOH. So the pOH in this case would equal 14 minus our pH. So that's going to give us 14 minus 4.82. And that is going to be 918. Now, again, I'm going to use either the pH at this point to get the H+ concentration, or I can use at this point the pOH to get the OH- concentration. So I'm going to take this and go that the H+ concentration equals the inverse log of the negative pH. Again, when you put that into your calculator, most likely a 10 and a caret will pop up. You want to make sure you do the negative 4.82. And if we do that on my calculator here, hit the right button, negative 4.82. We're going to end up here with, we'll call it 1.5 times 10 to negative 5, if I counted those zeros right. We do need a molarity there as it is a concentration, so it should have units. Any questions on that there? Now, at this point, you really still have two options. You could use kW and take 1 times 10 to the minus 14 and divide it by that number. Or you could do the same sort of calculation you did with the POH here. And you could do that the OH minus concentration would be the inverse log of the minus POH. That again is going to give you kind of like a 10 and a caret minus 9.18. And that would get us, looks like a 6.6 times 10 to the minus 10. Once again, we do need a concentration unit there, which would be molarity. This would be acidic, basic, or neutral. This would be acidic. You want to look at the pH here. So it is going to be acidic. Again, a couple reminders. There is only one answer to that question. So it shouldn't be acidic and basic at the same time, the same solution. I've never had anybody kind of go all three, go acidic, basic, and neutral at the same time. But what usually will happen sometimes is people will look at the pH and go, it's less than 7, it's acidic. Then people will look at the POH and go, hey, it's above 7, this is basic. They actually do run opposites of each other, the pH and the POH scale. If you have a high pH, you have a low POH. And if you have a low pH, you have a high POH. So they are actually opposites of each other. Most people have the pH scale in their head, so that definitely is the one you should look at in most cases. And again, never give all 3 answers or 2 answers, just one. Any questions on any of that there? Other thing that we also talked about last time in terms of that sig fig sort of situation, our pH there had 2 decimal places. So our concentrations really ended up with 2 significant figures. So again, going back and forth on those, you do want to kind of follow those same rules. Any questions on any of those? Yeah. What's that? It is acidic because you would look at the pH here. That's 4.82, and that is less than 7. You could also, in this case, look at the H plus and OH minus concentration like we did previously. Should give you the same answer if you want to look at that. But really, the pH is probably the easiest one to look at. Other questions? All right, let's take a look then at the second one there. And in this case, we actually have the OH minus concentration, which is 2.5 times 10 to the minus 7. So really, I'm just going to go right into the POH because I can do that. That's minus the log of 2.5 times 10 to the minus 7. Remember, we want to make sure we use our exponent button properly here. So I'm going to do a little log 2.5 minus 7. Looks like we will end up with a 6.60 as our POH. Now I could very easily get the pH because it should be 14 minus the POH. And that would give me 14 minus 6.6. And that would then get me like a 740. And really at this point, we have a couple of things we could do. We could use the pH that we just got to get the H plus concentration. Or again, you could just roll like we did earlier and use KW here. And we could use that relationship if we wanted to. And again, they both should get you really the same answer. So in this case, if we did the H plus, it would be 1 times 10. Oops, not the sin. There we go. Minus 7. Looks like 4.0 times 10 to the minus 8 molar in this case. And in this case, it would be Slightly acidic at this point with the 7.4. There we go. Again, following the same rules that we were talking about in terms of, again, sig figs, we had 2 significant figures there. That meant 2 decimal places really on these numbers. And then obviously we would disable this 2 on that guy as well. Any questions on any of those there? Yeah. All right, then let's take a look. I think we might have a couple more here. Let's do this one here. We have the H plus is 3.5 times 10 to the minus 6. What's the pH, POH, and OH minus? Have the H plus given to us. So really off the bat, we could do 1 of 2 things. We could either get the pH or we could use KW and get the OH minus concentration. I'm going to choose here to get the pH first. So it's going to be minus the log of our H plus 3.5 times 10 to the minus 6. That is going to get us here. Minus the log 3.5 to the minus 6. That's going to get us a 5.46. Once again, 2 sig figs, 2 decimal places. At this point, again, we could go with the POH, which would just be 14 minus that number. And if we do that there, it looks like 854 on that. And again, at this point, you do have some options. I'm just going to maybe just use our POH here. So our POH, our OH minus would equal the inverse log of the minus POH. So once again, that is a 10 and a caret minus 8.54. Going to give us 2.9 times 10 to the minus 9 molar. At this point here, this would be acidic, right? Again, the pH here is less than 7, so it should be acidic. Okay. Any question on it? Calculating that? Yeah. Yeah. There's only 1 decimal place because sort of in this situation, if we follow kind of where we started, we had 2 significant figures in the original concentration, which means when we calculated the pH, we should end up with 2 decimal places. So that also carried over here to the POH, which 2 decimal places. Going backwards, because we had 2 decimal places in the POH, that means 2 significant figures in the concentration. So remember, again, it's sig figs to decimal places, but if you're going backwards, decimal places to significant figures. So that does have 2 significant figures, but only 1 decimal place. Other questions? All right. So let's talk a little bit about acids, strong acids, weak acids, and some of those things. First off, acids and really bases as well. They are or can be strong electrolytes or weak electrolytes. As you may remember, electrolytes are really substances that break apart in solution and they produce ions, and they also conduct electricity, right? Depending on if it's a strong electrolyte or a weak electrolyte. A strong electrolyte will 100% break apart in solution. So something like sodium chloride is a strong electrolyte. In solution, 100% of what you have floating around are just the ions. You have none of the sodium or chloride units basically still together. A weak electrolyte, on the other hand, pretty much will stay together, but it will produce a few ions. So this is acetic acid, which is a weak acid. This will be mainly what you have in solution, but you will produce some of these. So because it is able to produce some ions, in the case of acetic acid, it's still able to produce some H+. It's still considered an acid, but it is nowhere near an acid, a strong acid like hydrochloric acid, which pretty much will 100% break apart into H+ and Cl-. So 100% of it will break apart into this. There's no HCl units still left in solution. So it creates a lot of free H plus really quickly, which is why it's a strong electrolyte. Also why it has a one-way arrow as opposed to our equilibrium type reversible reaction arrow that we see with weak electrolytes. Here are some strong acids. Hydrochloric acid, again, in solution is going to 100% break apart into H3O plus and Cl minus. Nitric acid will break apart into H3O plus in this case, and some nitrate. Again, here we're actually producing H3O plus because we are showing the water in the reaction. In this case, we would have H3O plus and some perchlorate. And lastly here, we have a little H3O plus and some HSO4 minus is good. So in this particular case, we could, like I wrote up on top, show the same sort of dissociation as simply HCl breaking apart into H plus and Cl minus. So again, they're equivalent, just showing the dissociation. There is a list of several strong acids, which these are part of, that you really should know. And then pretty much everything outside of that will probably be a weak acid if you had to make a guess. So a list, just to list some of these here, which are listed there below. Sulfuric acid, perchloric acid, hydroiodic acid, hydrobromic acid. So those 6 there are pretty strong sort of acids. Some weak acids like we see here listed that are commonly come across, acetic acid, hydrofluoric acid, nitrous acid, hydrocyanic acid. So these are some examples of weak acids. I would say, like I mentioned a second ago, pretty much if you kind of commit these guys to memory, you're probably going to be in good shape of, okay, it's not one of those guys, it's probably a weak acid. So those are pretty much your strong acids that you commonly come across. Any questions on that there? So in the case of our strong acids, which are strong electrolytes in solution, this is 100% what we have is all the ions are pretty much present. We do not have any of the whole units basically still together. Now, weak acids, on the other hand, and there's a list of a few, will mainly stay together. And these guys will form similar here, H3O plus, plus F minus, H3O plus NO2 minus, H3O plus SO4 2 minus, and H3O plus OH minus. So again, in solution, unlike our strong acids, this is mainly what you got going on in solution. They're rarely staying together. Once again, you could also write this equation, taking the water out of it as simply HF going to H plus and F minus. So again, you write it that way. Now, strong bases are also strong electrolytes as well. They will completely break apart in solution. So sodium hydroxide, potassium hydroxide, barium hydroxide, these are all 100% what you have in solution is the ions. So because they produce a lot of hydroxide really quickly, they're considered a strong base. Bless you. Most of our strong bases come from basically group 1 or group 2 on the periodic table. That is because, right, group 1 is the alkali metals, group 2 is the alkaline earth metals, and the word alkaline means basic. Yeah, so if you make something alkaline, it's basic. So if you look at the periodic table, kind of like where lithium and sodium is, we go like sodium down to potassium, hang over there to calcium, up and down just a little bit. Any of those guys on the periodic table that have hydroxide in the actual formula usually will be strong bases. So kind of like sodium, potassium hanging right at calcium and kind of go down is usually where you'll find most of your strong bases, and they will have that hydroxide in the formula. Not all bases do contain hydroxide in the formula, and some can create obviously hydroxide as a result of a reaction. So weak bases, remember, if it's a base, it's going to accept the H plus in this case, in both of those cases. And it will make HF in this case and OH minus. It will always make where it comes from. So HNO2 and hydroxide in this case. So because this is a weak base, mainly in solution, you have these guys, but they are still able to produce a little bit of ions along the way, and then produce a little bit of OH minus, which makes it still a base in that case, but obviously a much weaker base than something like sodium hydroxide. There is an important sort of relationship that exists between acids and their conjugate base pairs and bases and their conjugate acid pairs. So there's a really sort of important relationship, and that relationship is this. If you have a strong acid, its conjugate base will be relatively weak. If you have a weak acid, its conjugate base will be relatively strong. So sort of an opposite relationship. If it comes from something that is strong, it will produce a partner that's relatively weak. And if it comes from something weak, it will produce a partner that's relatively strong. It also works with bases as well. If you have a strong base, its conjugate acid, which is its partner, will be relatively weak. And if you have a weak base, its conjugate partner, which is the acid, will be relatively strong. So just so we're clear, what we're really talking about here, and we'll see it in this chapter a little bit later on, but when we talk about sort of the conjugate base here being strong or the conjugate acid being strong, we're not talking about it in the sense of it being really like a strong acid or strong base. What it means is in certain cases, those conjugate partners can continue to react. And in a lot of cases, what will happen is if it is sort of a stronger conjugate partner, it will continue to react actually with water. And the result of that is it can have an effect on the pH. So that effect that it could have on the pH is a result of it either producing, actually, as we will talk about, more H plus or more OH minus in that solution. So if you have something that is relatively weak in terms of its conjugate base or conjugate acid, it pretty much will kind of be considered neutral. It will not continue to react at that point. But if you do come across a conjugate partner that is sort of relatively strong, it will continue to react and have an effect on the pH. H3O plus is the strongest acid you could have. OH minus is the strongest base you could have in solution. Any questions on that there? And we'll talk more about those guys sort of reacting a little bit later on in this chapter. So here's a table from your book. And again, you can see the opposite sort of relationship. These are our strong acids that we talked about, and the relatively weak partners are stronger bases and relatively weak acids on that side. So again, that sort of opposite combination. Again, a strong acid will 100% break apart. A weak acid will mainly stay together. So as you can see, mainly in this guy here, we have the HF unit together, a little bit of H plus and F minus, as opposed to over here where pretty much it's all ions that are floating around. All right, so if we do have a strong acid or strong base, let's try to calculate the pH of these guys. So what is the pH of a 2 × 10⁻³ molar nitric acid? And what is the pH of 1.8 × 10⁻² barium hydroxide solution? That is both a strong acid and a strong base. So sometimes you're not given just generic H plus and OH minus. So figure out the pH for each of these, see what you come up with. Okay, let's take a look. So again, like I said, they may not always sort of give you just kind of generic H plus or OH minus. You may actually be given some formulas of either a strong acid or a strong base, which is what we have in this case. So because nitric acid here is a strong acid, we do know that when it is in solution, it is going to 100% break apart into H plus and NO3 minus. Now, because we are interested in the pH here, we also know that the pH is equal to the minus log of the H plus concentration. That means in terms of the pH here, it is the H plus concentration that we do need to figure out if we're not sure. We do know that this is 2 times 10 to the minus 3 molar. That would mean the H plus concentration should be the same. It is 2 times 10 to the minus 3 molar because it is a 1-to-1 relationship between those two. By the way, the nitrate concentration would also be 2 times 10 to the minus 3 molar. Not that you need it in this case. If you remember from solutions and molarity, that is basically how concentration works. If you're not sure, here is the long version of that calculation: 2 times 10 to the minus 3 moles per liter of HNO3. Doing like stoichiometry and mole to mole relationship, 1 mole of HNO3 gives us 1 mole of H plus. Moles of HNO3 cancel, leaves us with 2 times 10 to the minus 3 moles per liter of H plus. So basically, if it breaks apart into a 1-to-1 relationship, it'll be the same concentration. Breaks apart into a 1-to-3 relationship, you multiply the concentration by 3. Yes, so that again is how sort of ions work. So now that we do know the concentration of H plus, that would be minus the log of 2 times 10 to the minus 3. And that is going to give me some number here, log. Go 2 to the minus 3. Going to look like 2.7 in terms of our pH in this case. Any questions on that there? All right, so calcium hydroxide or barium hydroxide here, also a strong base. So again, that's on that periodic table, kind of going that way there from group 1 to group 2, where potassium and calcium is with those hydroxides. Because this is a strong base, this guy here will also 100% break apart into a barium ion and 2 hydroxide ions. In this case, the important thing here for pH is actually the OH minus, right? Because that's going to allow us to get to the POH. And then from there, we could get to the pH of that solution. So to do that, we again need the proper concentration of hydroxide in this case. So we do know that this is 1.8 times 10 to the minus 2 molar. That means the hydroxide here, it's a 1-to-2 relationship. We should take 2 times 1.8 times 10 to the minus 2. And that would get us 2 times 1.8 to the minus 3. Will give us our proper concentration of 3.6 times 10 to the minus 3 molar. That would be our hydroxide concentration that we can now put into our POH. Minus the log of 3.6 times 10 to the minus 3. Looks like a 244. Remember, though, that that is the POH and not the pH. So one last step here, pH is 14 minus our POH of 2.44. And that gives us a much better looking pH that is basic of 11.56. Any questions on that? Yeah. Where did I get? I'm sorry. Yeah. It's a -3. It's just this part. Yeah. Are you asking how I got it, or are you asking is it a 3? It is. I think it is to -2 there, but the answer I think is 3. If let me just double check there. -2. So yep, it is. I'm sorry. So that is 2s. I think the answer is right. I think I just wrote it wrong there. Let me just double check there. No, it is not. Okay, my bad. I'm sorry. Take 2, try again here. All right. Okay, so try my calculator one more time. So we're going to take 2 times 1.8 to the -2. That is going to give us, so 2 times 1.8 times 10 to the -2 gets us 3.6 times 10 to the -2 molar. Thank you. And then that obviously is what should go into here. So we'll take the log of that. Gets us a 1.44. And subtracting that from 14 gets us a 1256. Thank you. Any questions on that there? So clearly write the right number, I suppose, or look at it correctly. Other questions on that? Okay, so again, it's a 1 to 2 relationship, so we do have to adjust the concentration. Obviously, like I mentioned, if it happened to be a 1 to 3 or something like that, you would multiply by 3 as well. I would say probably in most cases, in terms of strong acids or strong bases, you might have to do that adjustment probably mainly for your bases. Most of the strong acids are monoprotic, which means really the concentration of H plus and the acid itself will be the same. All right. There's our list of some strong bases and strong acids from your book. And again, as I mentioned, kind of group 1 over to group 2 and down is sort of where we have all those strong bases. And then there's our list of our strong acids. Now, when we're dealing with a weak acid, it is a little different how we have to deal with calculating the pH. So a weak acid, and by the way, if you ever need just a generic sort of formula for an acid, HA is usually the generic formula for a monoprotic acid. If you needed a diprotic acid, which has the ability to give away 2 protons, you could use this as a generic formula. And if you ever needed a triprotic acid, which could give away 3 protons, and you don't really have a formula, you could just use that as a generic. The difference between each of those is the negative ion. Remember that the cation in all those acids are H+, which means in this case, A has a -1 charge. In this case, A has a -2 charge. And in this case, A actually has a -3 charge. So when we do have a weak acid, it will set up an equilibrium. And we see our reversible reaction here with our arrows. And because it will set up an equilibrium, we could obviously write an equilibrium constant for it, which is known as Ka. I'm assuming for acid A would make sense. It is the same equilibrium sort of constant that we've been dealing with in other chapters. It is our products over our reactants. And once again, we would not include water in it. So if you were writing it based off of the top equation, like normal, you would not put the water in there, which is a liquid, and it would basically just be our products over our HA there. The Ka is, as the Ka value increases, the strength of the weak acid also increases. And that is because it is still a equilibrium constant value. And when we have a large value of K, does that mean we mainly have reactants or products at equilibrium? You have a large value of K. We mainly would have products. So in this case, if we had a larger value of Ka, we would have more products, and more products would mean we would have more H+ in the solution, and it would make it a stronger weak acid, right? Again, a weak acid is much weaker than a strong acid, but in ranking sort of weak acid to weak acid, the higher the Ka value, the stronger the weak acid it would be. Also, a really big hint of is this a weak acid or not is if you're given a problem with a Ka value, it is definitely a weak acid. Yeah, so it's very much what it is. Last thing you should also keep in mind as you go through this chapter definitely is if you're writing an equation, you got H+ on the product side. and you're doing any type of calculation, you should be using the Ka value. So those two things should always go together. You have H plus or H3O plus on the product side. That is definitely an acidic situation. And if it's a weak acid situation, you definitely should be using a Ka value. How do we solve sort of pHs for weak acids? We really do the same approach. So because it's a weak acid, it's going to set up the equilibrium. We need to do an ice table. The sort of additional thing that we do is we're really interested in most cases the equilibrium number there for the H plus, so that we could then go into basically the pH equation. So we would do these problems just like a normal equilibrium problem, which means if it's a perfect square, you can square it. If you want to make an assumption, you could assume it. You could do the quadratic, however you want to do it. But in the end, you usually have to take that additional step. A lot of times we're not interested in what everybody's concentration is at equilibrium. We really just want the H plus concentration, so that then we can then go into the pH equation at that point. Any questions on that there? Here's a table in your book, which you might have to refer to for problems of some Ka values along the way. So why don't you try one here? Again, you're going to work it the same way as a normal equilibrium problem. Additional thing is go into the pH equation at the end. To see what you come up with, same rules apply. 1 coupon per customer per visit. Okay, let's take a look and see how you're doing. So once again, a couple of things you don't want to overlook when you're looking at a problem. I see HF, which hopefully you know is an acid. If not, this Ka should tell you it's an acid. It also should tell you it's a weak acid. So again, you see the Ka value, or you find it in a table, you know it's a weak acid. That should automatically tell you that it should be ice table time here. So to do that, we're just going to dissociate our acid. Again, if you want to include water in the equation, you can. I personally am going to leave it out and just go with H plus. If you did include water, the only difference would be you would have H3O plus on the other side, along with the water, obviously, on the left. We're going to do our initial concentration here of 0.5. These guys will be 0 like normal. We're going to go minus X, plus X, and plus X. That means at equilibrium here, 0.5 minus X, X, and X at this point. Any questions here on the ice table? Okay, like normal, we're going to then use our Ka expression in this case, which would be our products, which would in this case be HF times F minus divided by HF. That would equal 6.4 times 10 to the minus 4. Putting our values in there, x squared divided by 0.5 minus x equals 6.4 times 10 to the minus 4. Once again, this is a smaller value for the equilibrium constant, which means we can assume x is equal to 0. Remember, it is only going to be really, in this case, the x that we're subtracting from a number. That's going to get us x squared divided by 0.5 equals 6.4 times 10 to the minus 4. I am going to multiply this to the other side and also do a little square root action on it afterwards. And that's going to give me 6.4 to the minus 4 times 0.5. It equals, going to do square rooting of it. And that's going to give me an x value of 0.017885. Remember, though, that if we do make the assumption, we need to check it. So to check it is really the initial concentration here, of what we're going to divide it by. So we're going to take that, divide it by 0.5, times it by 100%. And in this case, I think we should be good. We're about 3.6%. And that is less than 5, which means this check is good, right? So because this check is good, and really the only thing that we're looking for is the H plus concentration, we go back to our table and we see that that is basically what X is equal to. So in this case, X equals 0.017885. which equals the H plus concentration. We'll put a little molarity there. That means we could then go into the pH minus the log 0.017885. Going to give us a pH in this case here of 1.75, I believe. .75. Any questions on any of those steps there? So as you could hopefully see, it is pretty much, yes, ma'am. Why did I assume X is equal to 0? Because we did have a small value of K in this particular case. Because this value is small, that means that the change part here should also be relatively small. It should mainly stay together. So in those cases, remember, just like we talked about in the regular equilibrium chapter, you could make an assumption that X is equal to 0, and you don't have to do the quadratic. You can still do the quadratic again. It should come out the same if you wanted to go that route, but might save you some time here if you do the assumption. Other questions? Yeah. No, it's just the K value. Remember that sort of a large value of K is basically anything above 1, basically, or 1, basically, and above. So really anything below 1 for the K value, you could try, and it's considered a small value. In some cases it will work, and in other cases it may not work. So again, it's really important to make sure that you do check it afterwards to make sure that it does work. But it's really based off of the K value. And because technically K is a small value, what that means is when we reach equilibrium, this is really the guy that we should have there, which means overall, there wasn't a lot of guys or that much breaking apart. So the change part is going to be really, really small. So we basically will still have basically the same amount as we started with in terms of that. Again, we can't get rid of all the X's. Otherwise, obviously, we have nothing to solve for. But we're starting with 0 for those guys. So anything that it gains is relatively significant. Other questions? So to sort of illustrate that point, if we were doing our same problem here, but we actually started with a concentration of 0.05 rather than 0.5, we would have our same ice table basically set up. And we'll use the same K value there, which was, I believe, 6.4 to the minus 4. So if we did this with this concentration, the only real thing would change is we have basically that there. These guys would still be zeros. These would be minus X's plus X's. Gets us 0.05 minus X, X, and X. So really, it's kind of the same ice table, just a different initial concentration. We would then put it in like we did previously into our Ka expression. Would give us X squared 0.05 minus X equals 6.4 times 10 to the minus 4. Now, if we assumed X is equal to 0, that gives us X squared divided by 0.05 equals 6.4 times 10 to the minus 4. And if we do that there, 0.05 times 6.4 to the minus 4, and also take the square root of it. This would give us, again, multiplying and taking square root gives us an X value of 0.00565685. Now, if we take this and divide it by 0.05 and times it by 100, which was our initial concentration here, we actually end up with about 11%, right? Which would mean not so good. This assumption would not have been valid, and we could not use it. We would need to go back and basically solve it some other way, and that would be obviously the quadratic formula in this case. So as we'll talk about also in this chapter, the initial concentration is important, right? In the previous one, we basically had 0.5 versus 0.05, right? So basically 10 times or so the concentration we started with. So when we lose a little bit, it's not a big deal from where we started. But in this case here at 0.05, we're starting with a really small amount, right? So if we lose even a little bit, it is a much bigger change than what we started with. Kind of like a pizza, right? You get a brand new pizza, take one slice, not a big deal, right? You take a pizza that there's only 2 slices left, right? Somebody takes one slice, kind of a bigger proportion of what was starting with, right? So it's the same idea here. So this is a good reminder that you should definitely check your assumption if you make it, because it will not work in all cases, and you shouldn't just blindly kind of go with it in every situation. And also a good reminder that we do not make this type of assumption if the K value is a large value, right? Because that means basically the opposite is true. We would have a lot more products at equilibrium, right? So the change would be relatively big. Anything 5% or less than 5% really is the rule we're following here, which is the 5% rule, sometimes called. So anything basically but less than 5% is acceptable. Anything really kind of above 5% or 5% and above is considered a little bit too big. Other questions on that? Okay, so as we just did in this problem, as we've been talking about, we really solve weak acid problems, really just like equilibrium problems. We do ice tables, and again, all the normal things apply. If you have any solids, liquids, we don't include them. Is our stay aqueous is pretty much what you'll have in this case. Really won't have too much gas, I don't think. Really the only thing that we are a lot of times interested in is that H+ concentration, which allows us to get to the pH. We will ignore the autoionization of water. You may be wondering, what does that mean? Water itself is producing H+, right, in solution, and OH- as it reacts with itself, basically, water reacting with water. So there are certain points where you may get an H+ concentration from the acid that's in there. That's actually a lot less than just water itself doing its thing. So there are some books and some people that will kind of take that into account. We will not. So our assumption here in this class is if you have kind of like a weak acid or weak base type problem, we're really going to ignore any contribution from water basically to that H+ or OH-. We're just going to blanketly sort of assume that all the H+ that we see in the solution is only coming from either the acid, or all the OH- in the solution would only come from the base. So you may sometimes see that some books do it, and even like some solutions, they'll go, hey, water's H+ concentration is much larger than what you had, so that's what the pH is going to be. So we will definitely ignore that autoionization part of water. All right. I think actually that's a good place to lay it up for today, I think. All right, any questions on anything here?